Okay, now we're going to look at fluid resistance or fluid resistant forces. Fluid resistance is this force that a fluid, which can actually be a gas or liquid, for example, water is the liquid, gas is actually like the atmosphere. It's the force that a fluid exerts on a body that moves through it. And one thing about fluid resistance is kind of like friction, where it opposes the motion or opposes the velocity of the object. And if we want to get really technical, it's the velocity relative to the fluid. So I guess you can kind of imagine the fluid being stationary or some type of constant velocity, and then the object is just moving through it. If you were in the reference frame of the fluid, it's gonna, like, you're still, the fluid's still, but the object is moving with a velocity. That's the idea, the technical definition. Typically we write it in two forms, and I use capital D for the force, or the fluid resistant force, because it kind of reminds me of drag or the air resistance. Books like to use F sub D or lowercase f. I just use D. And I'm just looking at the magnitudes. This equation describes the magnitudes, not necessarily the direction, because when we do Newton's second law, I remember that we have to define the direction, and it could be positive or negative, so depending on what the direction is. So this is the magnitude. And notice that the fluid resistant force is dependent on K, which is just a constant, and V, which is the speed of the object. And that's something we want to take note of, is actually that there is a speed the fluid resistant force is dependent on speed, and as speed increases, the force will actually increase. So it kind of changes as time passes, which is interesting, because if the speed increases as time passes, the acceleration increases as time passes, which means the force, the force, increases as time passes. And that's something we actually haven't really looked at with any of these past videos, so now we're going to look at it now. What happens when the acceleration changes over time. And it takes two forms. There's this one, which is just proportional to the speed, and then this one where it's proportional to the speed squared. And I guess a lot of people like to, or like in reality, is kind of, this one's associated with slow moving bodies, or just like simply just a slow motion type of thing. Maybe just like dropping something in water is kind of like this form. And a fast one is like a super fast, I guess, airplane pilot, and we would use this one, the other form, where it's speed squared. So that means as we increase speed, the drag force increases much more faster with the second form than the first. And now I want to look at the graphs. Oops. Let me see what I did. There we go. So here are the graphs, and what I've drawn in black is what happens here. Let me write it here as a note. This, or any line that's black, indicates no air resistance, while the colored ones do. So this one and this one and this one is all about resistance. So I just want to look at simply just something dropping from the sky, where downwards is actually positive now. That's just the convention I'll use, where downwards is positive, so G here is actually a positive value. One thing to notice is that the acceleration just slowly decreases to 0, but it never actually gets there. It's going to be like an asymptote, where the horizontal asymptote is A0, A equals 0. And as a result, that means V also approaches something asymptotically, which is what we call terminal velocity, and that's when there's no acceleration, or meaning that the forces of whatever cancel out, or there's no net force. That's another way to describe it. And then we have the position, where the black line is kind of like a parabola, but the blue line is kind of like a slower parabola, but it actually turns slowly into a line. Maybe like from here on it's kind of linear. Because the velocity is staying constant or getting to constant, that means the slope of the position should actually reach a constant slope. So that's the idea of these types of graphs. But the main takeaway is the velocity, where it approaches this special velocity, t terminal velocity, and we're going to look at a case right now using that. So this is the case. it's skydiving. But now it's with air resistance. So now we're going to tackle a problem with air resistance, something we don't typically do with physics because all the problems are like ignore air resistance. So now we're actually going to be looking at air resistance. I guess the way to describe skydiving is, let's say I have this person here. Let's say he just jumped off, but this kind of doesn't look like he just jumped off. Let's say he jumped off right now. And so he has an initial speed of v0, which is 0, right? Kind of like drop from rest. I don't know why this leg looks like it's detached from him. There we go. Let me draw the other leg. So let's say he's falling in a fluid, which is basically the atmosphere. So I'm just going to draw the fluid as a bunch of air particles, or like dust. Kind of that's the idea, that there's stuff in the way that you're trying to go through. And let's say that the form we want to work with is this form, the magnitude. I'm just going to give you the magnitude of the resistant force, or the fluid resistant force. I just want to find, I guess, first let's find the terminal velocity. So let's look at this first. And then after we find the terminal velocity, let's look at the velocity in general. Or try to find a function that represents the velocity in general. So with the terminal fluid, or the terminal velocity, we have just two forces, the mass, or the weight, the weight, and then the drag force, which is equal to kV. And specifically at this, we need to make the important note that A is 0, right? Because if we look at the diagram right here, as we approach this, A is 0. So if we're actually at Vt, or V sub t, we're at A equals 0. In other words, that the net force is equal to 0. So we're going to use that right now. The net force is equal to 0. So that means, actually, let me define what, first let's define what direction positive should be. And I'm going to define positive to be the direction he's moving in, which is downwards. So this is a positive. So this means mg minus kv is equal to 0. This is now terminal velocity because it's no acceleration. If I solve for v, I get, let's see, mg divided by k, and that's the terminal velocity of this form. It's not always going to be given to you in this form that I gave you. It might be v squared. In this case, terminal velocity is different. Now we want to look at the regular, or the velocity in general. So if I were to do that, there's now acceleration, but the acceleration is changing over time. So I'm going to actually rewrite it as a derivative of velocity with respect to time. That's how I think of it, is because the acceleration is not a constant anymore. It's going to change in response to what the velocity is at every second. So now we have the same thing here. This is not terminal velocity anymore because it's we have acceleration changing. So from here we actually have a separable differential equation, and we're going to go through how to solve this right now. So I'm going to bring it over here. I'm going to scroll down a little bit more. So we have mg minus kv equals m dv dt, and the way we do it is bring all the terms with v on the side with the right side, and then move all the terms that are not with a v on the left side, and then bring the dt also over. So I have to bring this m over to this side, and I have to bring this whole thing actually over because there's a subtraction sign. So I have to bring that all over, and then I'm also going to bring the dt over by multiplying it. So in other words, we have 1 over m dt is equal to 1 over mg minus kv dv. And now we have officially separated the variables. We can now integrate. But now we're going to look at we're going to make a definite integral. So at time equals 0, I want to evaluate from once he starts jumping off all the way to any time I want, so time t. And then same with the velocity. Since at the time 0, the velocity is 0, the initial velocity is 0 on the lower limit and v on the upper limit. If he was actually already falling, and let's say his initial velocity was actually 1, then we would need to change the lower bound, and it's not always going to be 0, but in this case it is because he was dropped from rest. So now we integrate, right? This left hand side is actually easy. It's just t over m evaluate at these limits. And on the right hand side we need to do, I guess, a u sub. So u equals mg minus kv, du equals negative k dv. In other words, dv is equal to negative 1 over k d u. So it's equal to, I'm going to bring that constant out since like this, and then I'll just evaluate this right now. It's negative 1 over k natural log of u, but I'm just going to substitute u right now. So u is mg minus kv, and it's positive. We don't need to worry that it's going to ever be negative because it's always going to be positive, since the weight will never be the same as the drag. I mean, when it is the same, it's going to be 0, and we are never going to actually get to 0. So now let's see where we are. We're here, and I'll just evaluate this at these two. And then what we want to do now is let's actually plug it in. So I'm going to pull that constant out and just treat it like this. mg minus kv minus natural log of mg, and if we plug in v equals 0, then it's just mg. And then this is equal to, let me evaluate the left hand side. This is t over m minus 0 over m, or t over m. And then here we have our equation here. Let's see. Our next goal is to actually try to find a way to solve for v, right? Because we want a function of v. So let me just multiply both sides by negative k to get rid of that thing sticking out in front. So if I multiply by negative k, it's negative t k over m is equal to, now here I'm going to use a log property, right? When it's subtraction, it's kind of like the natural log of whatever is inside divided by the other one. This is just a log property, nothing fancy really. So here we want to get rid of that natural log. So we want to raise, or I guess put it as base e, right? So e to the power of. In other words, this cancels out. So e minus t over k divided by m, tk divided by m is equal to mg. I'm gonna, actually let me do that in the next step. Let me just write it like kt, because it just looks nicer. I don't know. So now we want to solve for v. So how do we do that? I can separate this fraction actually. This is a step I'll take. So kv equals mg like this. And this is equal to e negative kt over m. This becomes 1. So it's, let me just keep going through all the steps just to make sure we go through everything. And then now we want to solve for v. V, what is v? Let's see, I guess I'll bring this over and then bring this over. So it's going to be kv divided by mg is equal to 1 minus e to the negative kt over m. This should have an m in it, I forgot. And then to solve for it, let's multiply by mg over k. So like that, and we get a function, or we solve for v. See if I can scroll down some more. There we go. It is equal to precisely mg over k, 1 minus e to the negative kt divided by m, and this is the velocity given any time. So it's kind of like a velocity at any time t, and this equation I guess is important because it's our end result. So I'll highlight it just to show you. In fact, we can actually do something. Mg over k, remember that? We found that all the way when we saw the case with terminal velocity. So I'll just substitute that. So let me write our final result in light green. So Vt is equal to terminal velocity times the quantity 1 minus e to the negative kt over m. And that's how you can describe the velocity. And then if you want to describe the position, you just take the integral of this and I guess use the initial condition that where he started was position 0. And then if you want the acceleration, you just find the derivative of this to get acceleration. But this is the end result, and this is the end of the video also. So that's it about air resistance, yes. Air resistance or fluid resistance, and this is the general idea. You want to actually look at it in terms of terminal velocity and then not terminal velocity, and then we arrive at a derivation. So that's it for this video.